A quantum chip in California completed a calculation in 200 seconds. The same calculation would take a classical supercomputer 10,000 years. That result is not just faster, it is already telling you that the machine is doing something the old model of reality cannot comfortably explain. What looks like a speed advantage is really a mechanism problem, and the consequences spread from there. That one visible sign already tells you the system underneath is more complicated. The calculation is not happening in one place. The answer cannot be verified using classical tools. The machine is producing outputs that push directly against the assumption that reality has definite properties before you look. By the end of this case file, you will understand exactly what that clue means and why the surface gives you no warning before it does. We view quantum computers as faster machines, but through a forensic lens, quantum computers are not faster calculators. They are systems exposing a layer of reality that physics can use, but still cannot explain. To understand the mechanism underneath, we have to look at what the machine is actually doing when it runs. A classical computer processes information by flipping bits between 0 and 1. Each step follows a defined path. The answer emerges from a chain of logical operations that can be traced, checked, and repeated. A quantum computer does not work that way. It uses qubits. A qubit is not a switch. It is a sphere of potential states. Before measurement, the qubit exists in superposition, holding every possible value at once. When the machine runs, it does not calculate one path. It explores every possible path simultaneously. The correct answer emerges not from logic, but from interference. Incorrect possibilities cancel each other out like colliding waves. The right answer is what remains. Now look at the 200-second calculation. The task was to prove that a quantum machine could solve a problem no classical system could verify. The answer arrived. But the verification process itself would take 10,000 years. That gap is not a temporary limitation. It is a threshold. We are entering an era where quantum answers cannot be checked because the checking process would take longer than civilizations last. The machine is producing outputs faster than reality itself can confirm them using the old tools. That is not a speed advantage. It is a structural departure. The calculation is doing something that does not fit inside the classical model anymore. But that is not the only loss here. The deeper problem is that we do not know where the calculation is happening. Physicist David Deutsch argues that quantum computers get their power by performing calculations across countless parallel realities. The observed answer is not the result of one process in one universe. It is the final interference pattern from a computation distributed across the multiverse. The machine finds the right answer because wrong answers in different realities cancel each other out when the wave function collapses. If that explanation holds, then every time a quantum computer runs, it is borrowing computational power from versions of itself that exist in places we cannot see, touch, or measure. The calculation is real. The speed is real. But the mechanism requires a model of reality in which this universe is just one thread in a much larger structure. And the harder part is that the alternative explanations do not work either. For decades, physicists hoped that quantum behavior was just incomplete knowledge. Maybe particles carried hidden variables, secret internal instructions that determine their behavior in advance. If that were true, quantum mechanics would just be a shortcut, a useful approximation masking a deeper deterministic system. But experiments have ruled that out. The 2022 Nobel Prize in Physics was awarded for proving that particles do not have definite properties until the moment they are measured. There are no hidden variables. Reality is fundamentally probabilistic. The wave function is not ignorance. It is the system. That result closes the door on the simplest escape. The quantum computer is not revealing something we missed. It is exposing something that was never there to begin with. The system also shows that entanglement is not a local effect. When two particles become entangled, measuring one instantly determines the state of the other, no matter how far apart they are. Entanglement has been maintained between Earth and satellites over 1,200 kilometers away. Scientists have used light from ancient quasars, billions of light years away, to trigger entanglement experiments, ruling out every possible loophole. The correlation is perfect. The distance does not matter. No signal is sent. This is not communication. It is something deeper. The particles behave as if space itself does not separate them. Some theorists now believe that quantum entanglement is the actual physical force that creates the fabric of space and time. If that is true, then the quantum computer is not just calculating. It is manipulating the structure that holds reality together. To understand the system underneath, we have to look at what happens when the machine tries to stay stable. Quantum states are fragile. Any interaction with the environment causes decoherence. The superposition collapses. The calculation fails. Classical intuition says that adding more components to a noisy system makes it worse. But quantum error correction works the opposite way. By adding more qubits and entangling them in specific patterns, the system becomes more stable, not less. A logical qubit can be encoded across many physical qubits. Errors are detected and corrected faster than they accumulate. The noise does not destroy the system. It gets absorbed into a structure that heals itself. That should not be possible under the old model. Complexity is supposed to amplify failure. But the quantum system shows that complexity, when structured correctly, creates stability. The machine is not fighting decoherence. It is using decoherence as a resource. And that is the part that changes what we thought we understood about information, error, and control. The system is behaving in ways that classical physics says should not last. But it does. Now look at what the machine can model. A single molecule of caffeine contains a few dozen atoms. Modeling the quantum interactions inside, that molecule is impossible for any classical supercomputer ever built. The number of possible quantum states exceeds the memory capacity of every computer on Earth combined. But a quantum computer can model it directly because it does not simulate quantum behavior. It performs quantum behavior. Richard Feynman argued that because nature is quantum, we must build machines that speak that same language to understand it. The quantum computer is not a faster version of the old tool. It is a reality mirror. It runs the same physics that the molecule runs. The calculation does not approximate. It replicates. That is why quantum machines are being aimed at problems like nitrogen fixation, drug design, and materials science. These are not abstract puzzles. They are systems where quantum mechanics determines the outcome, and classical tools cannot see the mechanism clearly enough to predict what happens next. The quantum computer does not solve the problem faster. It solves it in the same language the problem is written in. Finally, we have to look at the group that is preparing for what comes next. A sufficiently powerful quantum computer could mathematically dismantle the encryption protecting nearly all global bank accounts, state secrets, and private communications. The security model used across the digital world relies on the assumption that certain mathematical problems, like factoring large prime numbers, are too hard for any machine to solve in reasonable time. A quantum computer running Shor's algorithm can break that assumption. The math is proven. The only question is scale. Intelligence agencies are likely recording encrypted data today to store it until a quantum computer exists to unlock it. This strategy is called harvest now, decrypt later. The data looks safe, but the safety is temporary. The encryption is not broken yet, but the mechanism that will break it is already being built. Institutions are now racing to deploy post-quantum cryptography, new mathematical structures designed to resist quantum attacks. But the transition is slow. The threat is not theoretical anymore. It is operational. The quantum computer is not just exposing a gap in our understanding of reality. It is exposing a gap in the infrastructure we built on top of that understanding. And that gap is widening faster than the fixes are being deployed. You, the viewer, should watch for 3 signs. First, watch for verification crises. As quantum computers solve harder problems, we will see more results that cannot be checked using classical methods. The answer will be trusted not because it was verified, but because the machine that produced it was trusted. That is a shift in how scientific proof works. Second, watch for wave function experiments that test whether observers in different locations experience conflicting realities. Recent extensions of the Wigner's friend thought experiment suggest that 2 people can measure the same system and get answers that are both correct but mutually exclusive. If that holds, then reality is not objective in the way we assumed. It is observer-dependent at a fundamental level. Third, watch for breakthroughs in quantum error correction. When a quantum computer can run a stable logical qubit for hours instead of milliseconds, the system will cross a threshold. It will no longer be experimental. It will be operational. And the consequences will no longer be theoretical. So here is the answer to the question from the beginning. This is what that clue means. The 200-second calculation is not just fast. It is evidence that the machine is accessing a layer of reality where computation does not happen in one place, where answers emerge from interference across possibilities, and where verification itself becomes impossible because the process requires a model of reality we do not have yet. That is not a projection. That is the system behaving exactly as the evidence suggests. Quantum computers are not solved yet, but that is the point. The machine works. The results are real, but the mechanism underneath is still pushing directly against the assumptions that classical physics was built on. Physics can use quantum mechanics. It can predict outcomes. It can build devices. But it still cannot explain why observation collapses the wave function, why entanglement works across any distance, or why the act of measurement forces reality to choose. The quantum computer is not just a tool. It is a clue. It is showing us that the surface of reality, the part we can see and measure, is not the whole system. There is a mechanism underneath that we can manipulate but still cannot comfortably explain. Most people see the calculation. Now you can see the mechanism.